Module 12.3, Acoustical Analysis of Speech, Part 1. When we are interested in the frequency components of a musical note, we use an FFT, or a frequency spectrum. Generally, this gives us most of the information we want, the amplitudes of the different frequencies that make up that note. The information will be mostly the same for repeated notes or different time locations in a note. When analyzing speech, however, the frequency information changes rapidly. Each vowel or consonant that we speak has very different frequency and formant content. Early researchers of sound realized that and knew that they needed a way for analyzing frequency and amplitude as they changed over time. So the sound spectrograph was invented. Originally, it was meant to be a way for deaf people to use the telephone. It proved to be so difficult to read that the military took over the research during World War II, and it became top secret. They hoped that it could be a way of sending coded messages that would be difficult or impossible for the enemy to decode. But at that time, it was too difficult for anyone to decipher, the variation between humans and repeated iterations of speech being so different. Once the war was over, the machine was declassified, and a great wave of research on speech began, with a tool that could help analyze the acoustics of speech. The output of the spectrograph is a spectrogram. It allows us to see three kinds of information at once. Frequency is shown on the y-axis, time on the x-axis, and amplitude is shown by the lightness or darkness of the pattern on the spectrogram. You can think of a spectrogram as a series of FFTs taken sequentially, then rotated so that frequency is up and down, and the sequence of FFTs ordered from left to right. The first spectrographs were extremely sensitive devices and tremendously expensive. Today, you have access to a number of free software programs that will create spectrograms. Audacity is one, and we will use Pratt in the lab. It is difficult to use the information in a spectrogram to determine what word or sound is being spoken, but it does give us information about the acoustic properties of a sound. Formants. Formants show up as dark bands in a spectrogram. Remember that darkness on a spectrogram means high amplitude. This is a spectrogram of the phrase, "I can see you." Formant bands are most prominent with vowels and other voiced sounds. You can see how the second formant changes dramatically with the I in I and the EU in CU. The mouth changes shape for all of these sounds, and the spectrogram clearly shows how these changes result in resonant frequency changes. There's been much research on formants and vowels. One of the main studies that codified the vowel-formant relationship was by Peterson and Barney. This study was updated in 1994 by Hillebrand, Getty, Clark, and Wheeler. They came up with a table of average formants for each vowel as spoken by men, women, and children. In the lab, you will compare your F1 and F2 values with the Peterson and Barney values. One of the parts of their studies concluded that all was needed for accurate identification of a vowel was that the first two formants were in the proper frequency range. There are non-vowel sounds that will display formant bands. They are called consonant continuants. They are m, n, v, z, and v. These are consonants that are relatively sustained. Like vowels, they will have formant bands on a spectrogram. Here's a spectrogram of the words moon river. Notice the formant bands in the consonants. Sibilants. Sibilants are sounds that are produced when air rushes past a raised curved tongue. S, sh, ch, z, and zh are all sibilants. They are mostly unvoiced sounds and are characterized by a lot of high-frequency content. Here's a spectrogram of the sentence, "She chooses shoes." Notice that the low formant bands are missing for all the sibilants except for Z, which is a voiced sibilant. Also notice that most of the sibilants have stronger high-frequency content than the vowels. There are other non-voiced sounds like f, and f that will have similar characteristics. These are all identifiable on a spectrogram. Plosives. Plosives are sounds that occur when a buildup of air is released from the mouth. T, p, k, b, ch, and g are plosives. On a spectrogram, a plosive shows up as a vertical band preceded by a band of silence. Prosodic speech. This refers to the changing of pitch to change meaning. We use inflection in speech to affect meaning. For example, if I ask a question, I will raise the pitch of my voice at the end of the sentence. One of the things a software spectrograph can show easily is pitch. Pitch is generally shown as F0, the fundamental frequency. And most of the time, it is lower in frequency than F1. Here's a spectrogram of the phrase, "You snore," spoken twice. One is a statement, and one is a question. The blue line represents pitch. Which soundbite is the statement, and which is the question? Differences between a waveform and a spectrum. A waveform gives you information about amplitude and time, and a little bit about frequency. For example, here are waveforms of a man and a woman saying apple.
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 The main difference that is visible is the spacing between waveform peaks. Which waveform has more space between the individual peaks? Since time is on the x-axis, more space between peaks would mean a longer period. How does a longer period relate to frequency? And who would have a lower fundamental frequency, a man or a woman? So, a waveform can give you information on the fundamental frequency or pitch of a voice. Now let's look at spectrograms of the same sound files. We can see the same spacing and time between the peaks that we saw in the waveform, but another thing is also apparent. The formant bands in the top picture are a little bit higher than those in the bottom picture. Let's add those formant lines. So, which spectrogram would be that of the woman? Not that easy to tell, but you could make a pretty good guess. Now let's add the pitch contour to the spectrograms. The left picture has an F0 of 190 Hz, while the right is 102 Hz. That is a clear giveaway that the woman would be on the left. So a waveform can give you information of fundamental frequency and amplitude, but not much else. A spectrogram has a lot more information. One of the reasons that it is difficult to identify the exact sound from a spectrogram is because each utterance of a sound is different. If you record yourself saying a word 5 times in a row, the spectrogram will look different each time. You'll be able to locate different parts of the word, but they will not be exactly the same. This is a spectrogram of the word pale, said 5 times. Notice that each one is slightly different. Similarly, if you have 5 different people saying the same word, those spectrograms will also be different. This is one of the things that makes voice recognition and synthesis so difficult. A few more interesting tidbits about formants and speech. Consider this. Each time you say a word, the frequency and time components are different. Sometimes a little and sometimes a lot. Sometimes you have a cold and your voice sounds deeper. Yet if someone who knows you heard you speaking, they would know it was you and not someone else. How can that be? How about this? Everyone has a different shape and size vocal tract and vocal folds. so everyone's formants are different. Plus, children's formants are different from women's, which are different from men's. Add to that the fact that in different geographical locations, accents are different. Yet even with all those differences, it's kind of amazing that we can understand speech. And even more amazing that your smartphone can understand you when you speak to it, and that it can speak back to you and sound very much like a person. Continued in Part 2.